this problem says we have an elastic collision. So in the before picture, we've got m1 and m2 heading towards each other with velocities v1 and v2. u1 and u2. Here we're using u for the initial velocities and v for the final velocities. After the collision, m1 and m2 are moving away from each other with velocities v1 and v2. And because this is an elastic collision, we are going to use the principle of conservation of energy. Which means, in this case, that the initial kinetic energy should equal the final kinetic energy, and this is because it's elastic. We're also going to use the principle of conservation of momentum. That is, P initial is equal to P final, and that is because we're doing a collision. Okay, so we are going to now end up doing a lot of algebra. So to say that the momentum is conserved, what we're going to need to do is say that the initial momentum is equal to the final momentum. So that is, the initial momentum is m1 u1 minus m2 u2, because I'm making that the positive direction. And the final momentum is going to be negative m1 v1 plus m2 v2, because moving to the right is still the positive direction. Okay, so let's work with this momentum equation just a little bit. We have two unknowns here, v1 and v2. I guess I'll go ahead and write down the conservation of energy equation. This one says that the energy before 1/2 m1 u1 squared plus 1/2 m2 u2 squared. Now notice kinetic energy is never negative, because even if we have a negative velocity, when we square it, we have a positive kinetic energy. So that should be equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Now, let me give myself a little bit more room. I'm not sure why I'm curving upward on that. 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So what we have here is two equations for two unknowns. And when we have two equations for two unknowns, one of the best ways to go about solving it is to use substitution. So I'm going to solve the top equation for v2. And the way I'm going to do that is I'm going to add m1 v1 to both sides and then divide both sides by m2. So that's going to give me v2 is equal to the fraction m1 u1, which is one of the things I started with. When I add m1 v1 to both sides, I get plus m1 v1, and then I still have minus m2 u2, and all of that is divided by m2. All right, so now we're going to take this and substitute it into there. All right, so let's see what that would look like. We have, all right, so start by, well, I guess I'm going to start by canceling the 1/2. Multiply this entire equation by 2. That's going to give me m1 u1 squared plus m2 u2 squared is equal to m1 v1 squared plus m2, and now I need v2 squared. So v2 is a fraction, and if we're going to square it, that means we square the numerator and we square the denominator. So this is going to be m2 squared, and the top is going to be m1 u1 plus m1 v1 minus m2 u2, the quantity squared. Now, you might be tempted to just square everything inside the parentheses, but that's not how squaring works. You may remember that if you have a plus b plus c squared, a plus b plus c squared, that pencil is doing weird things to me. A plus b plus c squared, that is not equal to a squared plus b squared plus c squared. Is in fact equal to a squared plus 2ab plus 2ac plus 2bc plus b squared plus c squared. It's like foiling, but you've got three terms. So you get a squared plus a times b plus a times c plus b times a plus b squared plus b times c plus a times, or c times a plus c times b plus c squared, and that gives you all of those terms. So now let's do it for real with our actual thing. But before I do, I'm going to multiply everything. Well, let's see. Before I do, I'll cancel one of my m2s. And then I'm going to multiply everything through by m2. So that's going to give me 1m2 u1 squared plus m2 squared u2 squared is equal to m1 m2 v1 squared plus, and now I have my thingy. So I'm going to have a squared plus b squared plus c squared. So that's m1 squared u1 squared plus m2 squared v1 squared plus m2 squared u2 squared. Okay, and then I'm going to have, and by the way, this is plus because the negative squared becomes positive, but then I'm going to have plus 2ab, that's m1 squared u1 v1 plus 2 ac, well, okay, but that one's going to be negative, so plus 2ac is going to be negative m1 m2 u1 u2 minus 2 bc, which is m1 m2 v1 u2. Okay. Well, only one of these terms cancels. I've got an m2 squared u2 squared on both sides. So it simplifies a little bit. But this thing is a quadratic equation for v1. So there are terms. Is there just one term with v1 squared? No, there are two terms with v1 squared. there are 2 terms with V1, and there are what's a good another color? Orange. There are 1, 2, 3 terms that don't have a V1 in them at all. So we are going to rearrange this to make a quadratic equation. So let's start with the things that have V1 squared in it. So I guess I'm going to say 0 equals, and I've got an M1, M2 plus M2 squared times V1 plus, now let's look at, V1 squared. Now let's look at the ones that have just V1 in it. Those I underlined in blue. So we're going to have 2 M1 squared U1 minus 2 M1 M2 V1. No. U2 times V1. Okay, those are the 2 purple ones. All right, and then plus the 3 orange terms. M1, M2, U1 squared plus M1 squared U one squared. Sorry, that first one is going to be negative because I brought it over from the left-hand side of the equation. Okay, and then M2 squared U1 squared. And then minus two M1 M2 U1 U2. All right, so this is my A. This is my B. And this is my C. So I've got A V squared plus BV plus C equals 0. So that means that V1 is equal to minus B plus or minus the square root of B squared minus 4AC all over 2A. And, you know, if I was a real mathematician, I would substitute in these equations to solve this thing. But I am going to cheat a little bit and figure out what these numbers are. So grabbing my calculator, A is equal to M1, M2 plus M2 squared. So that's 0.5 times 1 plus 1 squared. Sorry. 0.5 times 1 plus 1 squared is 1. Sorry, plus plus m1 squared, which is 0.5 squared. 0.5 times 1. This looks like a 2. Where did it come from? It came from here, which came from here, which came from here. So yes, it's definitely supposed to be an M1. Okay. All right, plus 0.5 squared. So this A is equal to 0.75 kilograms squared. B is equal to 2 times m1 squared, that's 0.5 squared, times u1, which is 1.5, minus 2 times m1, 0.5, times 1, m2 times u2, 2.5. So B two times 0.5 squared times 1.5 minus 2 times 0.5 times 1 times 2.5 is negative 1.75 kilograms squared meters per second. That's a 7. All right, and then C, C is equal to negative m1 m2 u1 squared plus m1 squared u1 squared minus 2 m1 m2 u1 u2. Plug that all into my calculator, and I get C is equal to negative 4.3125. Now, this equation stays the same if I multiply both sides by a constant. So if I multiply the entire equation by 16, then this will become negative 69. This will become negative 28. And this will become 12. So I like 12, 28, and 69 better than 4.3125, 1.75, and 0.75. But either way you plug this in, you'll get the same answers. So I'm going to plug in 28 plus or minus the square root of 28 squared plus 4 times 12 times 69 plus, because the negative cancels with the negative 69, all divided by 24. That is a squared. And when I do that, I get two answers. I get that V1 is equal to either 23 over 6 or negative 3 over 2. And if V1 was negative 3 over 2, that means that M1 is still moving forward at 3.2 or at 1.5 meters per second. And if we plug that in, we would find that V2 was negative 2.5. And basically what that would mean is that the after picture looks identical to the before picture, meaning that basically there was no collision. If the after picture looks identical to the before picture, then both momentum and energy are conserved, and that would make sense, but it's not the answer to our problem. The answer to our problem needs to have a positive V1, that this thing is now moving to the left, so we can rule out that answer. And now we can go plug in for V2. Looking at this circled equation, V2 is equal to M1, which is 0.5, times U1, which is 1.5, plus M1, which is 0.5, times V1, which we just figured out is 23 over 6, minus M2, which is 1, times U2, which is 2.5, all of that divided by M2, which is 1, and we get that V2 is equal to 1/6 meter per second. Or, if we put this in the correct number of significant digits, V1 is equal to 3.8 meters per second, and V2 is equal to 0.17 meters per second. All right, let's check the rest of this to make sure what do we need to put in. Any special case or empirical laws. We use some definitions, the definition of momentum and the definition of kinetic energy, but we did not use any special case equations, so this is not applicable. And did we plug in any numbers that weren't explicitly given in the problem? Things like g is equal to 9.81, or if it started at rest, the initial velocity is 0, and the answer is no. All the numbers we plugged in were the actual numbers given here in the problem, so this is also not applicable to this problem. So, evaluate our answer by putting it into context with an appropriate reference. Okay, the final velocity of mass 1, which is 3.8 meters per second. Now, what could I compare that to? I could compare that to the initial velocity of mass 1, which was 1.5 meters per second. I can compare it to the initial velocity of mass 2, which is 2.5 meters per second. Or I could compare it to some external reference, like, for example, the walking speed of a human, which I know is about 1.5 meters per second. So the final velocity of M1, 3.8 meters per second, is more than the average walking speed of a person, 1.5 meters per second. Okay, and there is an example problem of an elastic collision, and you can see why we don't do these very often. There's a lot of algebra involved. Not too bad, though.